Welcome back to our discussion of synchrotron radiation. We are in the process of understanding what the spectrum looks like for radiation, synchrotron radiation, from a power law distribution of particles, where we have particles, electrons in this particular case, that have a distribution of energies, where the number of particles as a function of the energy falls off as this power law. And we previously derived what the spectrum looks like for a single particle. And then we said in the first video of this little segment, let us look at some physical insight, or get some physical insight from this. And we found that just from some physical arguments, that a power law distribution of particles results in a power law synchrotron spectrum. And then we said, well, let us do this a little more rigorously, a little more mathematically. And so we are in the middle of that process where we wrote down the explicit convolution or the integration of the synchrotron emissivity, or emission per unit frequency, over the distribution of particles. We integrated over the distribution of particles. We were able to pull out the frequency dependence for the most part, and we have our power law index. And indeed, that power law index matches the index that we found just from the our basic analysis. And then we have this tiny little but slightly annoying integration that we did not finish doing. And we said, well, in some cases, this works out to, it kind of goes away, and in some cases it's a little more involved, and then we left it there. So in this video, we're going to look at how that integration, how that integral gives us slightly different power laws and slightly different regimes, and how it kind of amends the synchrotron spectrum. A lot of this discussion is sort of in the weeds of synchrotron radiation, and if you're just looking to apply all of these formulae, then you can sort of go through this fairly quickly. But I figured I'd give you all of these details in case you were interested in knowing how all of this works out mathematically. So going back to this integration, then we have the synchrotron emissivity at a particular observing frequency omega. It depends upon the magnetic field, the charge and mass of the particle, and then we have the part that is the actual spectrum. It's in here. And then we have this integral of a function, which itself is the integral of a function, but let's not get into that. It's integrals all the way down. Okay, anyway, and then we have limits here. And of course, the part where we kind of get a little stuck is that these limits now depend upon this variable, this frequency that we're interested in. And then this is a chain of logic of how it depends upon that variable, right? So this x min and x max, it corresponds to omega, which is this observing frequency, divided by gamma 1 squared omega naught and gamma 2 squared omega naught respectively, where gamma 1 and gamma 2 are the limits of this power law. And this omega naught is just the frequency scale. And for our purposes, the most important part is that this doesn't depend upon the Lorentz factor, or the frequency, of course, itself, the observing frequency, I mean. So for our purposes, this is just a constant. Later on, we'll be integrating over pitch angles, and then it will no longer be a constant. But for now, this is just a constant, so it just sets the frequency scale. So right, so x min and x max are the integration limits. These are, you can call them x1 and x2, corresponding to an omega 1 and omega 2 that are down here, which I've written up here. They are just, omega 1 is the characteristic frequency of these electrons, omega 2 is the characteristic frequency of these electrons. And I don't have the expression for the characteristic frequency explicitly, but it's literally just this times gamma squared, right? So omega's characteristic of gamma is omega naught times gamma squared. Right, so let us see what this expression, what this integration does, or what this integral does in a few different regimes. So there are three different cases to consider. So one case is x min is much greater than 1, and if you think about it, because x min is always less than x max, right? Through this, you can check that for yourself. In fact, feel free to pause this video here and check for yourself that x min is always less than x max. Right, so you'll find that x min is always less than x max, which means that if x min is much greater than 1, then x max must also be much greater than 1. So this is one case. Then another case is x min is much less than 1, and x max is still much greater than 1. So now one is much less than 1, the other is much greater than 1, and you can see what kind of limits you might take in that regime. And then a final case is if x max is much less than 1, which then implies that x min is much less than 1. I've just written them kind of reversed, but once x max is much less than 1, it will push x min to also be much less than 1. So either both of these are much greater than 1, both of these are much less than 1, or this is much less than 1, that's much greater than 1, and those are the three cases we'll talk about. Now, of course, there are the possible cases. One of these could be of the order of 1, but all that will happen in that case is that you'll get transitions between the different spectral regimes. So these will determine the three spectral regimes. We'll talk about that in a second. And then any other kind of values of X min and X max will just give you transitions. So these are the asymptotic regimes that are relevant. So you can think about, I'll just quickly discuss this example, and then we'll discuss this in some detail right now, and then I'll leave this one, where both of them are much less than 1, as an exercise for you. So in the case that both of them are much greater than 1, then this is much greater than 1, and this is much greater than 1, then what happens to the integrand? Right, so remember this f of x has a particular shape, which is that it is of the, or it looks like x to the 1/3 e to the minus x. Right, so for very large values of x, the exponential dominates, which means that for very large values of x, when x min and x max are both much greater than 1, this f of x inside the integral, the x is much greater than 1, which means that f of x is basically like an exponential. And so for those very large values of x, basically that exponential is going to kill the integral, which means that this integral is very, very small when x min is and x max are much greater than 1. And for that reason, this synchrotron emissivity falls off, and you can show it falls off basically exponentially for very large frequencies. So frequencies above omega 2. So when you're far above the omega characteristic of this gamma 2, when you're observing at much higher, very high frequencies, higher than the frequencies at which these electrons radiate, the spectrum is going to cut off exponentially. So that's intuitively what you might expect the spectrum to look like. This one, case 2, is a little more complex, and at the end of the day, it's going to give us a power law back. And so let's look at that particular case. So let's consider the case that x min is much less than 1, and x max is much greater than 1. So just as to connect back to what these x, I mean, we should look at x's, like what does that mean? Let's get a sense of what we're talking about when we talk about these x's. So remember that x min is nothing but omega over gamma 2 squared omega naught, and so that's much less than 1. And this is omega over gamma 1 squared omega naught, and that's much greater than 1. And so that means that our observing frequency omega is much less than gamma 2 squared omega naught, and omega is much greater than gamma 1 squared omega naught, which, if you put these two together, just means that gamma 1 squared omega naught is much less than omega is much less than gamma 2 squared omega naught, which is the same thing as saying that omega is between omega 1 and omega 2. Right, so omega 1 is gamma 1 squared omega naught, omega 2 is gamma 2 squared omega naught. So if you're looking at the spectrum of this radiation, then I'm going to draw it here. So here I'm plotting the spectrum p omega as a function of omega. Then there is, in the spectrum, there is a omega 1, which is the characteristic frequency of these electrons. There is an omega 2, which is the characteristic frequency of these electrons. And we are in this regime where omega is between omega 1 and omega 2, so we're looking in this spectral region over here. So in this region, and you're far from the edges of this regime of validity. And in this case, as you might expect, this integral should fall away, and it should give you back just that term in front. And in fact, that's what happens. And this is fairly straightforward to show. So I'm just going to write down an expression to demonstrate to you how that works. So in this region, where x min is much less than 1, x max is much greater than 1, you can effectively take the limits of this integral from 0 to infinity. Why can you do that? When x max is much greater than 1, you're in the exponential region anyway. And so you're going to, the contribution of the integral is going to be very small for very large values of x. And then for very small values of x, note that you have an x to the p minus 3 over 2, and so you have small contributions times x to the 1/3. And so very small values of x also, you get very small contributions. So we can write this integral as the integral. So let me just look at the integral. So the integral gives you, let's say, 0 to infinity time of f of x to the p minus 3 over 2 dx. And so that's just the integral. Now, what is this? This is just a number, right? Because f of x is a function of x. It's a known function of x. It's again, as I said, an integral. But it's a known function, and you can hit it with something, and you can integrate it out again. In general, and this is what I call a rabbit hole. So I'm just going to write down the how to do this sort of integral. It's not going to be hugely relevant in terms of being able to do this, generally speaking, but let me just tell you what it looks like. So the general form of this sort of integral is if you have x to the mu, some quantity mu, f of x dx, you're trying to do this integral from 0 to infinity, then this is a standard integral, and its solution is as follows. It is 2 to the power of mu plus 1 over mu plus 2 times gamma, this is the gamma function, it's not a Lorentz factor, of mu over 2 plus 7/3 times gamma of mu over 2 plus 2/3. This is an identity for this f of x. It's an integral identity for the f of x. And this gamma function, you may have seen these gamma functions before. If you're not familiar with them, you should just remember that you might have seen that gamma of n is n minus 1 factorial. Right? So for integral arguments, this gamma is just that gamma function. But for these non-integral arguments, this is some number that you can calculate. So in our case, our mu is p minus 3 over 2, so you can put that into this expression, and that will give us the expression for J sin of omega that I'm going to write down here. So our J sin of omega in this particular case is root 3 e cubed b sin alpha over 8 pi squared epsilon naught c me, and then there's an n naught, and then because of this mu plus 1, we get a p plus 1 here. And then we have an omega over 2 omega naught to the power of 1 minus p over 2. And this 2 comes about because we have this 2 to the mu plus 1, which I've absorbed into this omega over omega naught here. And then various gamma functions. So it's gamma of p over 4 plus 19 over 12 times gamma of p over 4 minus 1 over 12. So this, in all its glory, is the full emission coefficient for synchrotron radiation from a Pauli distribution of particles. And here we have, for all our trouble, all of this in the last several minutes, is what we've got out of it is this p dependence here. So this is like a correction factor, a p-dependent correction factor, but this holds the physics. Like this is the actual spectral shape. It's omega to the 1 minus p over 2. And so that is why now in excruciating detail we can see that the spectrum here has a power law slope of omega to the 1 minus p over 2 as long as you are in the regime where you're in between omega 1 and omega 2, which are the characteristic frequencies of the gamma 1 and gamma 2 electrons, respectively. So I know that that's possibly quite a lot of different bits of information, a lot of integrations. So feel free to pause this video at this point and see that all of this makes sense to you. You can check that this substituting mu of p minus 3 over 2 gives you this expression when you substitute that. Okay, so the next thing we're going to do is look at the fact that so note that this is the emission coefficient, which we'll discuss this in when we get to synchrotron self-absorption, but this is a thing that we stick into the radiative transfer equation. This will tell us how much energy is being produced and how, and then it propagates, of course, and we'll have to account for that. And if you are not familiar with the radiative transfer equation, don't worry about it, we'll get to it later. But this is the amount of energy any volume of space containing n naught electrons produces as a function of frequency. If you want to know the emissivity, then we need to integrate this expression over all solid angles, because this is radiated into different solid angles. And if you integrate over solid angles, then that means you need to integrate over this pitch angles alpha. So you need to integrate over different angles that the pitch angles that the particles can have. Okay, so thinking about that, and also another reason you will want to integrate over pitch angles is because in any physical system, it's highly unlikely that all of these particles are moving at the same angle alpha with respect to the magnetic field, have the same pitch angle. So that's, I guess, actually the main reason that you'll want to integrate over these pitch angles. So to integrate over pitch angles, we need to know what quantities in here depend on the pitch angle. So that's what you're going to do next. Have a look at this expression. Feel free to pause this video and have a look at this and see what quantities depend upon alpha. Okay, so the next thing we're going to do is we're going to integrate this expression over pitch angles, and we're interested to know what depends upon alpha. So of course there is explicitly a sine alpha in here, and so this thing obviously depends upon alpha. But then let me use a different color. So this thing depends upon alpha. But then another thing that depends upon alpha is this omega naught. So now it was nice having the omega naught, but we're now going to have to break it apart into its constituents, which is the 3qb over 2m, and then that's sine alpha. And so when we integrate over alpha, we're going to have to do let's see what our J-sin dependence on alpha is. So there's a sine alpha, so it is proportional to this sine alpha. And then there is a sine alpha in here, and that is to the power of 1 minus p over 2. So it's really sine alpha to the power of p plus 1 over 2. So what we need then is we need the angle average of this quantity over sine alpha. And really at this point, we need to assume something about the angle distribution of particles. Right, so, and what we're going to do is we're going to assume that the particle distribution is isotropic in pitch angles. So there are an equal number of particles moving at some angle alpha compared to some other angle alpha. And if you didn't know this, if the particle distribution is not isotropic, then not only do you need to know this d and d gamma, but you would also need a d and d alpha, or d and d sine alpha if you like. But we are not going to go into that level of detail. We're going to assume that it's an isotropic distribution of pitch angles. And so all we're going to do is do an angle average of the sine alpha. And so that looks simply, that angle average looks just like this. It's the average of sine alpha to the power of p plus 1 over 2, averaged over all solid angles omega. You've probably done angle averages like this. The way to do that is it's the integral of this d omega divided by the integral of d omega. The integral of d omega, of course, is just 4 pi. So it's 1 over 4 pi times the integral of sine alpha to the power of p plus 1 over 2 times 2 pi sine alpha d alpha. And here we've simply taken our polar direction to be aligned with the z-axis, and so your theta in the d omega becomes the alpha direction. And so now you have sine alpha to some power of p plus 3 over 2. So this is 1/2 the integral of sine alpha to the power of p plus 3 over 2 d alpha. Now this is also a standard integral. The value of this integral is root pi over 2. And then there's additional gamma function, so it's gamma of p plus 5 over 4 divided by gamma of p plus 7 over 4. And so feel free to pause this video at this point and have a look at the relevant sections of the books, which are as follows. So this equation up here for J sin is 8.86 of high energy astrophysics, and it is also equation 6.36 of Rybicki and Lightman. With the one difference being that, remember, as I think I mentioned, that this book does high energy astrophysics. Instead of having d and d gamma in terms of gamma to the -p, it has the energy of the particles to the power of -p. which means that there are various factors as a set of MC squared running around. So in this expression, in this equation, the corresponding equation for this, in that book, there are various factors of MC squared to various powers of P. And there will be a kappa instead of an n naught, and that's because of that slightly different definition of the normalization. And then this equation over here is equation 8.87 of high energy astrophysics. And so feel free to pause this video over here and have a look at the relevant sections of the books. So if you put all of this together, then our expression for the emissivity looks like this, and I'm going to write this here and hope that I don't run into that diagram on the other end. So our epsilon sin, this is the emissivity of omega, is √3 e cubed b sine alpha. Nope, no sine alphas. Remember, we integrated those out. So we're done with the alphas. B n naught over 16, these two, pi squared epsilon naught CME. And then, unfortunately, we have to give up our omega naught and break it into pieces. So now we have m omega over 3 e p to the power of 1 minus p over 2. Is he going to make it? We'll see. Root pi gamma, and then there's this gamma stuff. So it's gamma p plus p over 4 plus, that's just p over 4 plus 19 over 12 times gamma, well, I'm going to have to go down here, gamma of p over 4 minus 1/12 times another gamma function. I'm going to remove this because you remember that. So we don't have this DNT alpha, so we've just done this angle average here. Right, and then there's this one. So it's gamma p over 4 plus 5 over 4 divided by p plus 1 from here, and then that gamma. So that's gamma p over 4. I'm getting Lorentz contractions in my gammas, plus 7 over 4. And this is equation 8.88 of high energy astrophysics, and I do not dare draw a box around it because I'm going to run into that diagram over there. But so this is the expression that I'm going to maybe make a bracket for you so you can see that this is a key equation. So this is the synchrotron emissivity of a power law distribution of particles. It tells you how much radiation per unit volume is being produced by by particles. And I say per unit volume, it is per unit volume, but then it depends on how many particles there are in that volume. That's why there's an n naught over here. As an aside, sometimes this n naught becomes a source of great stress and trouble for people who are calculating how much radiation you get, because you need to figure this out, and this is the number of, when you're talking about relativistic shocks, is the number of particles swept up by the shock, and then there are various normalization issues. So if you do relativistic hydrodynamics, you'll have to deal with that, like figuring out what the n naught is. But for now, that's the number of particles that are radiating in that volume. You have the charge on the particles, the mass of the particles. The most important thing, of course, remember, is that the emissivity is proportional to the frequency to the 1 minus p over 2, which is how you get that power law. And then there is all of the stuff which is just a p-dependent correction. So if you know p, which is of the order of somewhere between 2 and 3, then that's just a number, and you can tabulate that, so you don't have to keep calculating it every single time. So that brings us kind of to the end of the discussion of the calculation of the emissivity. Now I said that that's only case 2, and there is a case 3, which is what you would, what the spectrum would look like if you are at the regime that x max, oops, I am missing 1, is much less than 1, and x min is also much less than 1. And then you can show that that corresponds to this regime down here, where you're much below this lowest frequency. And what happens there? That is an exercise for you. And feel free to try that and see what you get. All you need to do is set the corresponding expressions for x min and x max, which is much less than 1, and then use this power law expression for f of x. See what that power law looks like for small values of x, and then just do the integral. And you will actually find that there is for the integral to converge, you need a particular, there's a constraint on the value of p. P cannot be arbitrarily small, because if it is, then actually the integral diverges. And so that indeed establishes an additional constraint on p that we don't always talk about, or sometimes we might forget. And so that's important to keep in mind, or can be. And then you'll see that the result of that is an additional power law regime in the spectrum, and you can demonstrate for yourself that that power law regime here corresponds to omega to the 1/3 power. And you can show that explicitly, and then you can also think about, or I encourage you to think about why that makes sense. Why is it 1/3? And for that, think about what are the electrons that are producing the radiation at those frequencies.